I would like to tell you a short story about the study I have been doing recently, which is an attempt to summarize data on the modern fire activity. I'm in historical records and then the chronology is the way this interest is realized. We do reconstructions of fires based on fire scars, though it's very interesting because this is the time when we'll have probably the highest, at least in terms of the climate. In Canada, it makes perfect sense to understand climate-fire interactions. Though in Europe, and specifically in Northern Europe, this is somewhat of a challenge, partly because the fire activity in European section of the boreal zone is mostly controlled by humans, or at least suppressed by, due to the very high population density, large road network, and history of forest use, which is the forest which is now fragmented, and that this continuity of fuels will have in Canada. So records of this type, records of fire activity, are often of suboptimal quality, have non-climate signals, and sometimes simply short, because surprisingly enough, in many parts of the Europe, records of fires haven't been kept in a proper way, and only small segments are available for analysis, like readily available for analysis. So this study was an attempt to make a synthesis of available data, try to improve this data, extend it, and again, look at the climate-fire interactions. So this is the area we looked at. It's a broadly understood boreal forest of Northern Europe, stretching from Norway in the west to the... You see there are different forest types or vegetation types covering this area. As with any boreal, important part is that it's dominated by coniferous species. In this part, it's mostly pine, Pinus sylvestris, spruce, Norway spruce, and on the eastern fringes, you have very little of larch. So the fires in this region are not always stand replacing. Of course, there are many places in the world where fires are not stand replacing, but thinking and working in boreal Canada, we used to think of fire as something which destroys the stand completely. While in this case, it's really somewhat different. We'll have a proportion of fires which are really destroying the whole stand replacing fires, but majority of them are of mixed severity, meaning that you have a mosaic of surviving forest and destroyed forest after the fire run through. Another interesting feature of this territory is a very large difference in terms of the modern fire activity. I already mentioned that nowadays fire activity is largely controlled, but of course the control of fire activity means somewhat different things, whatever the area you actually look at. And if you look in the western fringes of this area, places like Norway, Sweden, Finland, well, you shouldn't probably call Finland a fringe, but anyway, on the west, then you will see that the fire cycle, which is the second to the last column in this figure, in this table, is extremely high. Fire activity is very low. The fire cycle is an aerial measure of fire activity, which is number of years equals to the period which fires need to burn this area, and the total amount of area which equals your study area. So the longer the fire cycle, the lower the fire activity. That's the basic pattern, or the basic principle. So in this second to the last column, you see the fire cycle as we have it from observational data in the second half of the 20th century. You see it's really at the scale of several thousand years. And in some cases, like in the case of Finland, it's up to close to 30,000 years, which is extremely long fire cycle, clearly not the natural one. And you will have extreme events when we'll have years where a lot of area burned. Then the fire cycle drops, which is absolutely the last figure on this. And what you see here is that it actually drops to the point that at certain parts of the region, like in Russian sections of the boreal zone, it gets pretty close to the value we typically reconstruct from dendrochronological records. So we're talking about just few hundreds of years. So it doesn't drop so heavily in the Scandinavia, for example, but for Russian forest, one can argue that these are the extreme events which actually make the fire activity being kind of resembling what we have in the historical reconstructed record. So it's of high relevance to look at the mean value in terms of monthly drought code or some other proxies of fire weather. So to handle all this diversity of the places, we normalized the data and we did the clustering. So the clustering resulted in 5 clusters. We defined actually 5 clusters a priori prior to the running the algorithm. And these 5 clusters, they were placed in this way. So we didn't really use any information about positioning, about coordinates of these regions during the clustering, but they happen to be grouped pretty well together, meaning that there's actually some natural coherency in the behavior of fire weather, despite the fact that these clusters involve different administrative units sometimes that go across the borders, and that involves a lot of differences in terms of the data collection routines and data quality and the type of the forest and so on. So that was a good result. So for this data, what we did, we took the best member of the cluster because we really trusted data which had strong correlation with the climate. So that was not very clear, so I can just re-articulate. We looked at the chronology of each cluster member and we contrasted it with the fire weather to see which one has the strongest correlation. We believe that those who have the strongest correlation has the strongest data quality, because why on earth fire weather wouldn't correlate with monthly drought code? Martin Jardin showed that it's almost a perfect way to represent fire hazard, climatological fire hazard on a large regional scale. Since we trust Martin, so we really took this assumption and use it as a criteria to select the best cluster member. And why just one member? Well, partly because we want to remove things which are highly correlated, because if you have 2 regions sitting close together, getting into one cluster, clearly their fire activity would be highly intercorrelated in time, and it won't be really providing some additional and interesting information for the further analysis. It will probably just be introducing some noise because one of the regions will have suboptimal quality of the data. So we decided to take one, and then what we did then, we looked at the association of this cluster with the climate. And to be more specific, we looked at the way large fire years when it burns really a lot in a specific cluster, represented by this best cluster member. We wanted to know if these years are associated with the pressure patterns, and actually they did. So here we'll have a pressure pattern at 500 hectopascal, the height of this pressure level, and we see we'll have positive anomalies across all clusters during the large fire years in each of these clusters, which tells us that the pattern is basically consistent with what we saw earlier. That is, it's a high pressure cell sitting in this region, sometimes not really centered on this region, but sitting somewhere on the edges of this region. And this may be important actually, because it may create more wind on the edge of the area on this high pressure cell, and the wind under the dry conditions, this is a very good thing to happen if you want to have very large fire. Typically, you don't want to have it, so you should say it's a very bad thing to have. But in terms of this study, it was kind of consistent. So we saw that the pattern is very stable, largely the same, and whatever cluster we take will have this high pressure cell. And in terms of this high pressure cell, this is a representation of something which is in Europe called Scandinavian blocking, which is one of the 4 typical weather types identified for Europe, for Northern Europe, and it's characterized by a high pressure developing over the Scandinavia and lower pressure developing down south. And you may wonder, oh, that sounds like an NAO pattern. Yes, it's close to this, but it's actually somewhat different because the geographical center dipole, the centers of action, they are slightly shifted. So it's actually called Southern North Atlantic Oscillation Pattern as NAO. Okay, our second interest here was to understand if there is a synchrony in appearance of large fires in each of the clusters. Quite often, if you read media, people say, oh, the amount of fire increases and fires become more widespread. You know, journalists, they really like this dramatic statements. And of course, nobody really tested that before. So what we did, we reconstructed fire activity for each cluster back to 1901, and I'm not going to go into how we did that. And then we selected upper 10% of distribution in the reconstructed amount of burned areas for each cluster. And then we run something called analysis to see if occurrence of the years when we have multiple regions demonstrating the large fire, if this occurrence has a trend towards increasing or decreasing. And that we also did some estimation of significance of that. So we knew that this occurrences this years when we had 4 regions or 5 regions or 3 regions showing large fire, this occurrence is above the frequency we can expect under the random process. So these are the red colors, that's the red bars, those who are above the expectation under the random process. And what we see actually nothing. We see there's no really pattern of increase or decrease in the occurrence of large fires across this region, meaning that we couldn't really say that large fires become. Well, that was a negative result, and we tried to look at the same thing, but using only monthly drought code, something which is, again, the proxy of climatological fire hazard. When we did that, we saw that, again, there's no pattern. We thought, well, at least we'll have some consistency here. So we advanced to the next question. And the next question was to look at the trends. Now, I already told you that extremes are very important and mean values are of no relevance. But here I changed my mind to tell you that it's still of some relevance. And why it's of relevance? Because, well, if you have different mean, the chance of reaching extreme is actually different. If you have a mean of 1 and you have a normal distribution with a standard deviation of 1, so chance of reaching 2 is not the same as if you have the situation when your mean value is 1.9. So means are relevant, but you have to understand why they are relevant. So they are relevant because they help the system, or they affect the chance for a system to reach certain extreme value. So in this case, we looked at the temporal trends in monthly drought code for this area, and we used the whole 20th century and a bit of the 21st century. And in case the trend was significant, we put a dot on this grid cell. And if trend was positive, that was the more like reddish color. If trend was negative, that was a bluish color. So in this case, what we see is that we do see some trends, but they're not very strong, though, and they don't cover the whole area. The only major part which we see here is the increase in monthly drought code early in the season more specifically in April, in the western part of the area. There's a clear trend covering almost the whole Scandinavian peninsula, but it also shows that the region is not homogeneous. We have parts which have absolutely nothing, we have parts which have very strong persistent trends. And this is something which actually proven by another analysis. In this case, we took July monthly drought code, because typically July monthly drought code is well connected to the fire activity, whatever region you take. And we looked at principal components. Sometimes they're called orthogonal, empirical orthogonal functions, but originally it's a principal component analysis. And what we see here, we see a kind of, again, non-homogeneity of the region. We have some regions which show a positive correlation between principal component and the monthly drought code, and some parts show negative correlation. So it means that behavior of monthly drought code in July, and more or less the same pattern we see if we just average for the whole summer, is not really the same, it's not synchronized. So some regions, when they get really hot, it gets not so hot, I would rather say it gets cooler and less fire prone on the other side of the region. So again, it shows that the region is not very homogeneous. And finally, we looked at the correlation between index, which is actually the index representing all clusters, which is like region-wide fire activity index based on actual data, on actual fire data, not on some climatological fire hazard, but on actual data. And what we saw here is that there's a more of a precipitation impact, and the precipitation impact is more consistent spatially, because we have only negative correlation between precipitation and fire activity index. Though in case of temperature, we have a pattern which indicates that temperature is not really, there's both negative and positive correlations within this region. And absolutely the last thing I'd like to show you is that as we saw this pattern of pressure fields, I think that was the one, this one. So we thought we really need to look at the summer North Atlantic oscillation. And indeed, it showed a positive correlation with this fire activity index. It wasn't very strong. The R-square was 0.17. But if you look at R-square as something which is composed of two correlation coefficients, which are at the scale of 0.4, so then you can think that it's decently high correlation. So despite the fact that we have quite a diversity of conditions, as I just showed you, we do have a large-scale circulation anomaly or circulation pattern, which does show a correlation with our fire activity, like region-wide fire activity. So to conclude, I would say that probably the future is uncertain, and to a considerable degree, that would probably be dependent on the way the circulation anomalies will evolve. And modeling of these anomalies would be quite instrumental in understanding the future fire risks. Thank you.
Thank you very much, Igor. Are there any questions for Igor right now? If there are, you can either use the chat, or you can raise your hand, or you can also turn on your microphone and ask him a question. Thank you.
And then I should start. Igor, I have just a question. So, because you work indeed in Sweden, but also in Canada, so do you compare the fire dynamics and do you see big differences? Or, for example, the dynamics you see is very local. I was wondering.
Well, yeah, I mean, I wouldn't call it very local, but actually, when I was, I mean, that's a paper which I hope we will submit in a couple of weeks. But actually, one thing which clearly is on the agenda, exactly what you said, we really need to do similar analysis stretching from Scandinavia to the Russian boreal forest, Siberia, which is still Russian boreal forest, and then Canada. And I do have the data, I have the data for Russia, and I believe that should be the next big endeavor, because the larger the area you take, the stronger chances, the stronger are the chances you get a good correlation and better understanding with the pattern due to the what I'm saying. I mean, the larger the area you take, the stronger are the correlations with large-scale atmospheric circulation anomalies, or the SSTs, for example. So it does give us a hope that we will have a more clear signal, and maybe even can discuss something about predictability of the fire activity based on the circulation anomalies, which kind of progress in time and space.
Okay.
I don't know if I answered your question, but
no, indeed, it was a curiosity. That's true. But,
yeah, but that's exactly what I've been thinking and what I have been like planning for after this.
Okay. Well, thanks. I